All right, so go ahead and put questions in the chat window, or if you do want to, if you're comfortable voicing questions as they come up, feel free to voice them. Hoping we get more students to log in. Okay, so last time we started working on this problem, this was the one where we put, we had 6u of t minus 6u of t minus 1. So I'm going to give you some values to actually plug in. So we're going to let R equal 125 ohms, L equal 0.1, C equal to 4 milli, and plugging that in to this equation, we get an IC equal to 6s over s squared plus 2s plus 2500 minus 6s e to the minus s all over s squared plus 2s plus 2500. And solving for the roots of those, if you remember, the s will equal minus b, so minus 2 plus or minus the square root of 2 squared minus 4 AC, which is going to be 2500 over 2. And that gives approximately a minus 1 plus or minus 50j over 2. And so we can use that to plug in for the bottom. So we have IC is equal to 6s, and then this becomes 6 plus 1 plus 50j times s plus 1 minus 50j, and then minus 6 s e to the minus s over the same. And what we're going to use here to solve the rest of this is called partial fraction expansion. And note that this quantity is similar to the second quantity, except a minus and the e to the minus s. So minus is just going to be a constant that once we find the value for the 6s over that, then we can do the same, just take a minus of it. E to the minus, oh, there we go. E to the minus function in the s domain ends up just being a shift in the time domain. So all we're going to need to do is once we find it in the s domain, then we can take a minus of it and then just shift the constant or the function and the u of t minus by 1. So we just need to solve for this portion of the 6s over s plus 1 plus 50j times s plus 1 minus 50j. So to solve for this, we're going to use what's called partial fraction expansion. And what this is that we can say that this is going to be equal to a, some number a, over the first quantity of the fraction, plus b over minus 50j. So we're going to say that those two are equal. And then we want to solve for A and B. So what we're going to do is we're going to multiply both sides of these to get rid of one of these quantities, A or B. So if we multiply, copy them. So multiplying both sides by the same number. So say we multiply by S, let's see, S plus 1, this is J, and that's a J, cut those off, plus 50J. That's going to get rid of these, and then on this side, if I'm multiplying by that, S plus 1 plus 50J, that is going to make that one go away, and then this is going to be plus 50J in the top. And then if we let S equal to A minus 1, let's see, plus minus 1 minus 50J. And plug that in, we have S times minus 1 minus 50J all over a minus 1 minus 50J plus 1 minus 50J. And then on the right, we have A plus B times minus 1 minus 50J plus 1 plus 50J. And we notice that the top part of this goes to 0, so that will get rid of so this is going to equal 0. So you have a minus 1 plus 1, and then a minus 50J plus 50J. So that will go to 0, and then A is just going to equal this left side. So that gives us A is equal to a minus 6 minus 300J all over the minus 1 and the plus 1 cancel, so minus 100J. And remember that rectangular form, A plus BJ, if we want to put it into exponential form, this is going to be the square root of A squared plus B squared, and E raised to the J inverse tangent of the imaginary part, which would be B over A. So this is rectangular form, and this is polar, and we want to move to polar form for this. So rectangular form you're going to use for add and subtract, and the polar form you want to use for multiply and divide. So in this case, you can use an online calculator to find this, or you can do them on the top and the bottom. So on the bottom will be minus 100 e to the minus j90. And j, remember, is just 90 degrees. Oh wait, plus, this would be a plus j90. And this is going to be 6 squared plus 300 squared, and then ej inverse tangent of a negative 300 over negative 6. And this ends up being 3e to the minus j 1.15 degrees. So the other thing I forgot with A and B, note that B is considered going to be the complex conjugate of A. So that means everywhere there's a j, you're going to replace it by minus j. So the complex conjugate just means that you replace you're going to replace everywhere there's a j with a minus j. And so you can see that A or B, or I should say B is the complex conjugate of A. So now that we have A, we can just take the B is just going to be the complex conjugate of it. Or you can go through those steps again. But with B being the complex conjugate of A, that's just going to be E, or 3e to the plus j 1.15 degrees. So now we can rewrite our ISC as A, which is 3e to the minus j 1.15 degrees, all over s plus 1 plus 50j, and then plus 3e to the plus j 1.15 degrees, all over s plus 1 minus 50j. And then we have a minus 3e to the j 1.15, and that's going to be multiplied by the e to minus s, all over s plus 1 plus 50j. Yeah, that didn't do well. Okay, it's not moving well. Okay, I'm just gonna erase these and write them again. All right, so this is add, subtract, and this is multiply, divide. All right, so, and then we need the last part of this, which is ej to the plus, oops, this one's minus, sorry, this one's plus 1.15 degrees, e to the minus s over the s plus 1 minus 50j. All right, so now we want to identify on the table the components that look like this. So going down to the tables, and we see on this one that s plus ajb having ej to theta and then ej to the minus theta is going to be the one we want to use. So I'm going to grab this one. And now we need to determine from this what is A and B. And so looking at this, what is your A value going to be? So we're going to do these two first, and then we're going to take this one and do these two next. So A here is what? Anyone? Thank you, Quinn. Yes, it's 1. B is going to be what? Correct, 50 and theta. Thanks, Carly. Positive or negative? So you look on here, this has a positive with a positive. This one has a positive but a negative. So we're going to have to take a negative 1.15 degrees. Do you guys see that? Hopefully you see that. Nobody's commenting. Okay, thank you, Quinn. Okay, so we're going to change this over. So this is going to be IC of t. And it's going to be 2e. And then we just said that a was 1, so minus t. Cosine b was said to be 50t. And then a minus minus, so a plus 1.15 degrees. And then this will be u of t. And then we have to take that minus, so put that as a plus, so this will be minus that whole thing. So we just take a minus of this, and then, oh, sorry, there's also a 3 times 3, and then a minus 3, and then all of these get shifted. So 2e, and then it gets shifted by a 1, so this becomes minus 1, and then the t gets shifted by minus 1. So it's going to be a minus t minus 1. Here, I'll go grab that. Oh, what happened to my pages? Oh, that was bizarre. Okay. Okay, why is this what I was working on? Okay, so this shift, grab this so you can see the shift. So the property for the shift so you can see here that the minus s, so we bring that into the function at t minus 1. And then the rest of the function, cosine 50, and then again this is t minus 1 plus 1.15 degrees. And then it's going to be u of t minus 1. So that second portion is all multiplied by ut minus 1. Okay, questions? All right, so goals today is to understand this partial fraction expansion, to manipulate the equation so that you can match it up with a form on the table. I'll hang out here for a minute. So the goals of this is to be able to manipulate these equations in the S domain so that you can then match them up to something on the tables. Otherwise, it gets to be a little bit more complicated to transform them back into the time domain. All right, Jagan, are you good, or do you need to see that still? Okay. All right. The other thing that I wanted to talk about is kind of poles and zeros of a circuit. So sorry. Looking through my notes. Okay. I'm going to skip the poles and zeros for a minute. Okay. Well, no, I will. Okay. So typically you're going to solve this. You're going to get a function that looks like this. It's going to have, or you want to reduce it down to what we can get to, which is the like s plus 2, s plus 4, s alone. And so you're going to want to put this in its fractioned. That word doesn't sound right now, but instead of the polynomial, you want to put it into the fraction form. Is that the right word for that? Whatever this form is. And so you're going to reduce it down to this. And then from there, you're going to use usually partial fraction expansion to then match it up with something on the table, because this won't match with anything on the table. So, but when you do this, this actually gives us some information about the circuit itself. And what it gives is in the top, you're going to get, these are called zeros of the system. And the ones on the bottom are poles of the system. And typically this function will be your output over your input, which I mentioned last time was considered your transfer function. And so the zero of the system is where that root is at 0. So in that case, your zeros for this one will be that s is equal to a minus 16 over 10. That location will be a 0. And then you're going to have poles. You're going to have one at 0, one at minus 2, and one at minus 4. And so what this will look like is that you will have this imaginary and real graph, and you're going to put a pole at minus 16 over 10 is like 1.6. Okay, so 0, minus 1, minus 2, 3, minus 4. So we have kind of 1.6, a minus 1.6 for a 0, do it in red. And then you're going to have the poles, you're going to have one at the origin, and they are x's typically, and then one at minus 2, and then one at minus 4. So this would be your graph of your poles and zeros of this system. What this actually translates into is that you have all of your poles and zeros are on the left as negatives, and this is going to be a stable system. And you're going to learn about stability in, I can't remember the new number. There's a control system class if you want to take that, where you learn more about stable systems or not, but we always try and have stable systems. So our poles and zeros, we want to either be at the origin or in the negative side of this imaginary and real. When you're in the right side of this, then you don't have you have usually a non-stable system, and it usually doesn't converge to a 0. What do you mean, Anthony, by the convolution theorem? I think so you're going to go, in ECE 3500, which is signals and systems, I think that's what you're looking at, is when you are looking at signals themselves and you want to, say, transfer that signal, you're going to actually convolute a signal with a carrier signal. So the signal will be like your voice signal, and then you're going to convolute those and actually send those over the wave system to, like for the cell phone, you have your cell phone, it actually convolutes your voice onto a carrier signal and then transmits that signal, and then it interprets that on the other side. I think that's what you're meaning by the convolution theorem. In here, we're not going to get into that. That will be ECE 3500. What I want you to understand, though, from this is the transfer function, and how you get the transfer function again is to solve your circuit with output is equal to your functions times your input, and then you divide your input to get an equation that looks something like that. From there, you can identify the zeros and poles of the system, and then we want to transfer this back into the time domain to see what the output time domain signal should look like. And then that time domain signal would be something we could multiply our input signal, but we would want to take that to the S domain, multiply it, and then transfer it back. Okay, so for this one, we want to find also the partial fraction expansion to turn this into the time domain. So this function we're going to have, it's going to be over each fraction. So a over s plus b over s plus 2 plus c over s plus 4. And then that is going to equal the whole function. So the first step is to multiply to get rid of one of them. So I'm going to just multiply by s on both sides. And then I'm going to let s equal 0. So when I do that, it's going to remove this from the bottom, put an s up here, and put an s up here, and that's going to remove that one on that side. With these being multiplied by s, these two are going to go to 0. And I will just have a is equal to 10 times 0, so 0 plus 16 over 0 plus 2 and 0 plus 4. So that gives me 16 over 8 for a value of 2. And then I'm going to do the same thing for b. So over here. All right, so for this one, instead of multiplying by s, I'm going to multiply instead by s plus 2. Just grab this so that c is easier to copy. All right, so this one I'm going to do s plus 2 on both sides. That will get rid of that one on that bottom. And s plus 2 on the top here. And then that will remove that one there on the bottom and s plus 2. And then I'm going to let s equal minus 2. And doing that, we'll put s as minus 2 will be minus 2 plus 2, so this will go to 0. And this one will go to 0. And I will have b is equal to 10 times minus 2 plus 16 all over minus 2 times minus 2 plus 4. And that ends up being a minus 20 plus 16 all over minus 2 plus 2. And so a minus 4 over minus 4 for a minus 1. Or sorry, plus 1. And then for this one is going to be your c value. So I'm going to take s plus 4 multiplied on both sides. And then I'm going to let s equal minus 4. And so that will get rid of these on this side. And this will go to 0, and this will go to 0. And so we'll have c is equal to 10 times minus 4 plus 16 all over minus 4 plus 2. And then minus 40 plus 16 is minus 24. and then a minus 4 minus 2 is a plus 8 for a value of minus 3. And so our function here is going to be 2 over s, and then b was a plus 1, so plus 1 over s plus 2, and c is a minus 3, and so minus 3 over s plus 4. And doing the inverse Laplace, let me get we have the 1 over s, and then we have this, which is a number over all right, so then the 2 over s, remember the 2 is a constant, so that will come out, and so it's just going to be 2 u of t. U of t, and then s plus 2 means a is 2, so e to minus 2t u of t, and then a minus 3 comes out, and then a in this case is a 4, so e to the minus 4t u of t. And that is my function answer. It should meet the same as the top one. 2 plus 2e to minus t, 2t, yeah. So that is the same. All right, questions on this? Okay. For this next portion, which is this one, whoops. This is where you have repeated roots. So in this one, your form is going to be a little different, and it goes, for this one, your form that you're going to transform it into goes a over, you start at the beginning one, which is 1, and then you have a squared of it, and then you have a cubed of it. And so with this one, there's a formula you can use, or I just like to pick several values. And so what I mean by several values is before we picked, like, we used s was the value of the root. And so you can do that one once, but then you have to choose different values. So I'll just pick like s is 1 or s is 0 or something that may simplify the right side of this. So I'm still going to multiply both sides. So I'm going to multiply by s plus 2. And by starting with cubed, that's going to get rid of it on this side, and then it will get rid of it here, and then I have s plus 2 squared, and then an s plus 2, and then I'm going to let s equal to minus 2 still, and that's going to put this one to 0 and this one to 0, and I can solve for c. And so c here will be 4 times minus 2 squared, minus 15, minus 2, minus 10. And that gives me a value of 36. 416 minus 30 minus 10 Or plus 30 minus 10, yeah. So 36. Plus 16, plus 30, minus 10, yeah, 36. And then I'm going to do the same thing, except for this time I'm going to take this. So now I'm going to use that value of 36 for C. Well, let's see. What was this? 4s squared minus 15s minus 10. Okay, so multiplying both these by s plus 2 cubed gives a times s plus 2 squared plus b times s plus 2 plus c, and then this is removed, minus 4s minus 15s minus 10. And so from here you can just pick different values of s. So if I let s equal 0, that gives me 4a plus 2b, and then I use the value of 36 for c, and 0, 0 minus 10. So I'm going to have one equation that's 4a plus 2b equals minus 46, and then I'm going to pick another one, let s equal 1, and that gives me 3 squared, so 9a plus 3b plus 36 equals 4 minus 15 minus 10. And then I can use both of these. So I can solve. This one I could put as solve for b. Let me solve for b. It would be a minus 46 minus 4a over 2. And then I can plug that b in here. And that would be 9a plus 3 times minus 46 minus 4a over 2 plus 36 equal to, what is this? Minus 25 plus 4 is minus 21. 25 minus 4, yeah, 21. And then I can solve these for a. So this is 9a. This will become 2 minus 2, so minus 6a is equal to minus 21 minus 36, and then minus becomes a plus. 3 times 46 over 2 is 23, and so 3a is equal to 12, and a becomes 4. And then go plug that one in for b, and that gives me a b is minus 23 minus 2 times 4 for a value of minus 31. So in the book they go through this repeated real poles where you can take the derivative of each one and then pick a value for the pole, but I like this method better, so whichever one you like, you're welcome to use. Going back up here, I'm going to put these in. So a was 4, so we have 4 over s plus 2. B was 30 or minus 31, and that goes over the s plus 2 squared. And then C was 36, and that goes over the s plus 3 cubed. And then translating that, we need to go find those with repeated roots. So we're going to have the s squared one. We're going to have 1 over s, this one. Oh, we have that one there. Okay. And then we need the squared one and the cubed one. Oops. All right, so the 1 over s plus a in the first one is going to be 2, and we multiply out of 4, so that becomes 4e to the minus 2t u of t. And then the squared one, our a in that case is 2, so we have plus t, or sorry, minus 31 first, so multiply out the constant, minus 31 t e to the minus 2t u of t, and then plus 36 t squared e, sorry, this was 2. I don't know why I wrote 2 minus 2t u of t. And so this is our final answer. Oh my goodness. Oh, I must have did a math wrong. 4e. Okay, I did math wrong somewhere with the 36. Saying that one's 18. Oh, so on this I forgot there's a 2. So because of this 2, you have to divide the number by 2, so there's going to be a half out in the front, so this becomes 36 divided by 2, which is 18. So that's where the 18 came from. Okay, and then that matches the answer. Okay, questions on any of this? You guys ready to do your own? All right, so try and do the partial fraction expansion and convert this into the time domain. I'll give you guys a couple minutes and then I'll go through the solution for this one. Okay, so for this one, we have to find the bottom first. So you gotta use the quadratic formula, and that gives you a minus 3 plus 4j. And then note that the roots are going to be, you're going to have a over that, and then b, which is going to be the complex conjugate of a, because it just has the minus 4j. So once I find a, I can translate it back to b. And so multiply both sides by the minus 3 minus 4j, and then that gives you, as you do that, a square root of 2e to the 45j. And then that would give you a minus 45j for b. And then note that it's going to be this form of the cosine b, t minus theta. And theta in this case is going to be a plus 45. B is going to be 4. Because you had 4j. Back up there. Here you go. 4j. So b is 4 and a is 3. And then that translates to 2 square root of 2 e to the minus 3t cosine 4t minus 45 degrees u of t. You could also use that additional transform that I gave, where it's as plus b over s squared plus 2as plus c. And then you have to note what what the capital A, capital B, a, and small c. And doing that, you end up with the same form, without having to do partial fraction expansion on that one. As I said, that cosine ends up being a very common one we use. So anyway, any questions on this? All right, this week there'll be a discussion on Thursday that you'll need to do, along with homework will be due Thursday, and then there'll be a quiz. And I think the quiz is on this partial fraction expansion. So make sure you understand how to do the partial fraction expansion. And I will see you guys on Wednesday. Hopefully I'll feel better and see you guys in person. All right. See ya.